We will now solve problems using the concepts we developed in the last lesson. A cell of EMF 1.5 volt and internal resistance 0.4 ohm is connected to a flash lamp bulb of resistance 1.5 ohm. You can see we are using a flash lamp bulb as an external resistor. What is the current through the filament? Now, if you remember, we had developed equations for external circuit, internal circuit, and the whole internal plus external. Do you remember those equations we developed? The equation for the external circuit is V equal to IR, that is the external. E minus V equal to I times small r is the internal. And if you add the two, E equal to I times R plus R is the total circuit. So you have the external circuit, internal circuit, and the whole circuit. Which of these equations will you be able to use here? We know the EMF, we know the external resistance, and we know the, we know the internal resistance. Well, we know EMF, we know internal resistance, then we know the external resistance. We need to find the current I. So obviously it is the entire circuit, internal plus external, that we're going to use here. Okay. So EMF equal to 1.5 volt, internal resistance R equal to 0.4 ohm, external resistance is 1.5 ohm, and we use the equation E equal to I times R plus R. That will be 1.5 equal to I times 1.5 plus 0.4, and solving that give me I equal to 0.79 ampere. Okay, another one. When a cell of EMF 2 volts is connected across an external resistance of R equal to 2 ohm, a current 0.625 ampere flows in the circuit. What is the internal resistance of the cell? Well, look at the problem and sort of figure out what you can do. We need to find the internal resistance of the cell. Well, we have developed a formula for it. For that, we need the EMF. We have the EMF. We need the potential difference across the external resistor. It's called the terminal potential difference. Well, we know the external resistor. We know the current in the external resistor. Can you use those values to find the potential difference? Yes. And those are the only quantities that we need. Alright, so here we have an external resistor 2 ohm and an internal resistance of 0.4 ohm. The EMF E equal to 2 volt. The external resistance is 2 ohm. And the current in the external resistance is 0.625 ampere. We first find the terminal voltage. That means the potential difference across the 2 ohm as V equal to Ri. We know R, we know I. That will be 2 ohm times 0.625. That is 1.25 volt. That is the terminal voltage across the resistor. We now know the EMF. We know the terminal voltage. We know the external resistor. We can now use the formula we developed for the internal resistance. Do you remember that formula? R equal to, lowercase r equal to uppercase R times E over V minus 1. Maybe R. Now the lost volt. Now I'm doing this to introduce that new concept. What is the lost volt? Lost volt is the voltage used in driving current internally through the cell. So if you now use that concept, you don't even need to use the formula for the internal resistance. The lost volt is the voltage used to drive the same current through the internal resistance R. So that will be 2 minus 1.25, 0.75 volt. Now this is the voltage used for driving current in the internal resistance. So now we can use the internal circuit to solve this problem. The lost volt is a measure of the voltage across the internal resistance. The current through the internal resistor is the same as the current in the circuit, which is 0.625 ampere. So using the internal circuit formula, what is the internal circuit formula? E minus V equal to I times small r. We know E, we know V, we know I, therefore we can find R, and therefore R equal to 1.2 ohm. You can get the same result by going through the formula for the internal resistance that we derived. Let's now talk about energy in an electrical circuit. Well, of course, the electric current flows in a circuit because energy is provided by the cell or the battery. And when the current flows in the circuit, energy is expended in the circuit. Alright, let's develop the concept of energy in an electrical circuit. A current in a circuit is caused by the motion of free charges due to the force they experience in the electric field that exists inside the conductor. Now, what is responsible for that electric field? Well, the electric field is produced by the potential difference between the two ends of that conductor. Thus, work is done by the electric field in driving charges around the circuit. If you now consider a conductor like this, electric charges are made to move inside the conductor due to the potential difference between the ends of the conductor. What is the definition of potential difference? Potential difference is a measure of work done per unit charge. If I say the potential difference between the ends of this conductor is 1 volt, what does that mean? It means to move 1 coulomb of charge from one end to the other, the work done is 1 joule. That is the meaning. So, work done by the electric field in driving charges, work is done in driving charges in an electrical circuit. This work done appears in the form of energy in the electrical circuit. So, energy in the electrical circuit is a measure of the work done in driving electric charges around the circuit. This energy might appear in the form of heat, light, motion, or any other form. We use electricity to produce many different kinds of energy that we require in our life. Is that right? Now, I am able to communicate to you because I am using electricity to produce sound, light, and many other forms. In other words, electricity is doing work for me. I am using energy from electrical circuits. Tell me, what is the definition of potential difference between the ends of the conductor? I want you to understand that very well. Potential difference between the ends of a conductor is a measure of the work done per unit charge that is transported across the conductor. If I say the potential difference is 5 volt, it means for every coulomb of charge that is moved from one end to the other, the work done is 5 joules. That is the meaning. Okay, if the potential difference between the ends of a conductor is 1 volt, it means 1 joule of work is done for every coulomb of charge that is moved from one end of the conductor to the other. Now here I have a conductor that has a potential difference of 1 volt between its ends. It means 1 joule of work is done for every coulomb of charge that is moved from one point to the other. That is the meaning that the potential difference is 1 volt. Alright, let's consider a conductor carrying a current I when the potential difference across its ends is V volt. Alright, we have a conductor here. The current in it is I. What is the meaning of that? The current is I. What is the definition of current? Current is the rate of flow of charge. So when we say the current is I, it means the amount of charge that passes through the conductor per second. In 1 second, there is I coulombs of charge going through the conductor. I ampere is I coulombs per second. Alright? And the potential difference is V volt, means for each coulomb that passed from one end to the other, the work done is V joules. That's the meaning there. The current is I ampere means that I coulombs of charge cross any section of the conductor in 1 second. And potential difference is V means that for each coulomb of charge that move from one end to the other, the work done is V joules. Alright? For each coulomb, the work done is V joules. Now, how many coulombs are passing through the conductor in 1 second? I coulombs. Therefore, what is the total work done in 1 second? The work done per unit charge is V joules. There are I coulombs. Therefore, the total work done will be V times I, so many joules in 1 second. Let's write that down. What is the total work done in 1 second when I coulomb of charge pass through the conductor? For 1 coulomb of charge passing through the conductor, the work done is V joules. Therefore, if I coulombs of charge pass through the conductor, the work done will be I times V joules. And this is the work done in 1 second. And what do you call work done in 1 second? So we say work done is I times V joules, and this is the work done in 1 second. Work done in 1 second is a measure of the power. Is that right? This is a measure of the energy converted from electrical to other forms in 1 second. Therefore, this is called the power in the electrical circuit. Work done in 1 second is what we call the power. So what is the equation for power in an electrical circuit? Power in an electrical circuit is I times V joules per second. What do you call that? Joules per second is a watt. So power P equal to I times V, and the unit of power is the watt, joules per second. Okay,